So, good morning everyone. Welcome to Midas Metro webinar series. I am Bodhi Rudra, Senior Technical Engineer from Midas IT, and today we are presenting the first webinar in the series of 3 webinars related to Metro Bridge Design and Practices. Today's session will be mainly focused on discussing Midas civil applications for metro projects and a brief introduction to rail structure interaction and its uses, why it is needed. Okay. So in today's webinar, the topics that we'll be covering will be a brief introduction to Midas will be given related to its engineering solution for those who are not aware of Midas. Similarly, the need of mass transportation systems. So why do we need mass transportation systems? What are the different solutions regarding mass transportation systems? The advantages and considerations for metro transportation. Balanced cantilever method of construction for metro bridges. And similarly, there is integral bridge construction method for monorail bridges. We'll also be discussing the main topic, that is the rail structure interaction for continuous weld rails, and a small touch to tunneling for metro subways using Midas GTS NX, and the different project applications done using Midas Civil. Also, the list of webinars, the other webinars that will be covered in the series, followed by the summary of today's webinar. So these are the topics that we will be covering in today's presentation. So more or less it will be an interactive session where I will be briefing you about the different technologies in Midas Civil related to metros, and how effectively the engineers have used Midas Civil for that. So to start with, I will be giving you a brief introduction to Midas. Midas IT is one of the leading software development and engineering solution providing company being used all over the world, and being related to the engineering consultancy services also. We understand the client's need properly, and by engineering solution, what I mean is that it provides a strong combination of sound engineering tools in all sectors of civil engineering, that is bridges, buildings, geotechnical and mechanical engineering as well, along with a very sound technical support and technical services that we provide. Also, Midas Civil, these are the total engineering solutions. By total engineering solution, what we mean is that Midas is actually involved in not only bridge engineering, not only building engineering, but also geotechnical engineering. So we can say that there is a perfect synergy between all the 3 fields of civil engineering, and all the engineers, the geotechnical engineer and the structural engineer, they all have interaction between different engineering tools. So for bridge engineering, we have Midas Civil, which is the major product of for bridge engineering, specialized solution from bridge engineering. Also for in-depth and more profound solution, we have Midas FEA, which is a finite element analysis software. Similarly, for building engineering, we have Midas Gen, specialized solution for building engineering again, and Midas Design Plus, which is a specialized design tool for design of columns, beams, staircases, cobbles, etc. And moreover, we have Midas GTS NX, which is again a finite element method and analysis software for geotechnical engineering. So we can say that all these 3 fields, all the softwares that are there, they correlate with each other. So they all act together to provide a complete engineering solution. This slide shows the major clients, the key clients of Midas for Indian market and the international users. So as you can see, almost all the leading companies like AECOM, Afcons, Gammon, Covi, CS2M Hill, L&T ECC, L&T Ramboll, Louis Berger Group, Mott MacDonald, right? And also RDSO, which provides the railway standards for Indian codes, and they have done quite a bit of work in rail structure interaction. And all the major PWDs like PWD Mumbai, PWD Chennai, and also railways like Western Railways, they are using the software quite effectively. Also, you can see major international users that are using the software, like again AECOM, Arup Industries, Atkins, Bechtel. They all are using the software quite effectively. So this was to introduce you to Midas. Now we step into the main gist of the webinar, that is mass transportation systems. So why do we need mass transportation system? One of the major concerns in today's world is that the population is rapidly increasing, which more will lead to considerable increase of road traffic. And in addition to that, poor traffic management and inadequate public transport, it worsens the situation. Also, day by day, we see more private vehicles in the traffic, and because of the inability of the public transport to meet the demands with the mass, and also because of the increasing incomes, we can say that there has been an increase in the number of vehicle ownerships. So due to these reasons, it leads to a reduced access to all the locations. Also, it leads to traffic congestion and pollution, which more or less causes a lot of road stress. So as a solution, we have different types of mass transportation systems, that is as follows. So we have metros. Similarly, we have monorail, tram, bus rapid transit system. Also, we have local railways. So as you can see in the figure itself, this shows the Mumbai monorail, and this is the Delhi metro. Similarly, the local railways for Kolkata and Ahmedabad BRTS. So these are the main major types of mass transportation systems that are used. Out of these, the most popular ones are metros and monorail, which we will be discussing thoroughly in the webinar today. So why do we require metros? What is the need of metros? First of all, metros are very cost effective. That is, they only require 1/5 energy per passenger per kilometer as compared to that of road-based system. So it leads in the terms of fuel economy. Moreover, it also leads to a considerable decrease in road stress because it causes lesser road traffic and thereby leading to far less accidents. And it doesn't require any road space. And when we are constructing underground tunnels, it doesn't require any road space, whereas for the elevated bridges, it will occupy a maximum of 2 meters width of road to accommodate the piers and other structures. Since metros work on electricity, it doesn't cause any pollution also. So in a way, we can say that it increases the overall mobility, as it provides a more comfortable, easy and better accessibility to facilities in the influence and remote areas, and it leads to more increased opportunities in the economic and business sectors. So these are the major advantages of metro. But what are the considerations? What are the major challenges that the metro rail design engineer faces? Okay, so there are some difficulties or challenges for metro design engineers, as it is very difficult to construct the bridges or tunnels in locations with very dense population, with the areas with urban settlement, where the relocation of the population is a difficult task. Also, while during the construction, there will be some noise, and the duration of construction, it may disrupt the flow of traffic and also stall it during the period of construction, which causes a lot of public discomfort. Also, metros and monorails, especially for metros and monorails, they use continuous welded rails, which can lead to excessive axial stresses, which needs to be properly considered using rail structure interaction. So these are the challenges for a metro rail design engineer. So how do we come to a solution for it? What are the solutions for it? So the solutions will be the construction procedures that we adopt. So we can adopt a segmental bridge construction procedure. So we can go for a balanced cantilever method of construction. So I will be discussing the balanced cantilever method in a few slides. Similarly, we can go for integral bridge method of construction for monorail. Okay. So both these things can be simulated using Midas civil. Also, for the continuous welded rails and the rail and deck interaction, we can go for again Midas civil rail track analysis module. Okay. And tunneling, mainly for the subways, the metro subways that we are constructing, we can go for Midas GTS NX. So there you can have tunnel boring machine, you can simulate the tunnel boring machine. Also you can bore through, you can simulate the hard rock and soil conditions. Okay, so these are the major solutions for the due considerations that we gave in the last slide. So we'll be discussing each and every solution one by one. So what is a balanced cantilever method? Balanced cantilever method is also known as the free cantilever method, which, as you can see in the slide itself, it implies the construction of cantilever segments from a pier in a balanced fashion. So what you can say that if this is our pier, okay, and these are the subsequent segments, so we construct the segments equally on both sides. It means that. So in a way what we can say is that the segments on the right hand side, it counterbalances the moment on both sides. So it doesn't require a separate formwork or anything to support these segments. So the advantage is considerable less formwork is required, considerable less false work is required. Okay, so also the construction procedure as follows is that I will be discussing in the next slide how the construction procedure is followed. So the balanced cantilever method, a balanced cantilever bridge will be typically looking like this, somewhat like this. So we have the PSC segments. What we do is that we start by, we can go for a cast in situ or precast segments. So we start by constructing on both sides together from both the piers. So at the end, there we have to stitch both the ends together. So this is one end, let this be the one end, let this be the second end. So we have to stitch these two together. So in order to do that, we have the stitch segment. So this is a typical balanced cantilever bridge. So what are the advantages? The advantages is that far less space is required, because in construction, for the construction in urban area where temporary shoring or formwork could disrupt the traffic services below, there you can go for balanced cantilever, because it doesn't require so much of formwork, it doesn't require any formwork for the segments. Similarly, it is very useful for larger spans. So if you have a very long span which cannot be, it cannot be launched, the launching of girder is not that much adequate, so you can go for balanced cantilever. Also, it is quite efficient and it can easily adopt to any curvature, or it can easily adopt any super elevation. Okay, and for different type of sections like tapering sections you have, it is quite good for tapering sections. So these pictures might clear why it is required. So for an urban settlement, for a traffic, it doesn't disrupt the traffic at all. So the traffic flows on its way and the construction is going above. So it doesn't disrupt the traffic at all. Also, the construction over railways, like railway lines are there, so it can easily be constructed over the railway lines also. Okay. Also, for it is very suitable for longer spans. If you have longer spans, in that case it is very suitable. Also, you can see here that you can go for a tapering sections. Okay. So what is the consideration for a balanced cantilever bridge now? We have discussed the advantages of balanced cantilever bridge, but there are some considerations for a design engineer for a balanced cantilever bridge also. Because one of the major consideration is the camber effect. So why the camber effect comes? Because as you remember that we had two piers, right? So we start by constructing the segments on each pier. So we start by constructing the segments one by one. So this is one by one. So because of the cantilever action, the segments, they don't remain horizontal. Okay, it will try to deform with the loading, with each loading of the segment, it will try to deform as a cantilever action. Similarly on this end also. So while we are doing the stitch segment, suppose if this is the stitch segment, while we are doing the stitch segment, the two cantilever ends should be perfectly leveled. There shouldn't be any deformation, any differential deformation occurring for both the ends. So in that case, the camber becomes very important. So we need to construct the segment in a particular camber. So in a particular camber we need to construct. So due to the cantilever action, at the end of the construction, this becomes perfectly level. So this is the camber. Similarly, we need pre-stress losses. So we need to check the losses for the pre-stressing, because in balanced cantilever more or less we'll go for staged pre-stressing. So in staged pre-stressing, differential pre-stressing, we need to consider the differential pre-stressing effect. Also the creep and shrinkage effect. Also we need to properly simulate the construction sequences, the construction stages for the balanced cantilever. So all these things, we need a specialized engineering solution for this. So Midas Civil comes as a specialized engineering tool for the design engineer. So what does Midas Civil specialize in? Midas Civil, as you can, of course you can create the bridge from scratch. You can create the nodes first, you can create the elements in between, and then the segments one by one. But also we have a specialized wizard for balanced cantilever bridge. So in the wizard, as you can see here, we have the bridge layout. Okay, so in the bridge layout, already the layout is mentioned there. So the wizard acts like a an interactive Excel sheet. So you can give a material properties, the number of piers, the pier section, the curvature in plan. Okay, the method of construction, like you're going for a cast in situ or a precast method of construction. Also the pier table age, what are the different ages of pier table, what is the duration of each stage. Okay, also we can go for tapering sections. We can also define the section properties in the wizard. So you can go for tapering sections, the diaphragm sections, all these sections you can create in the wizard itself. And finally we can go for the tendon profile also. So in tendon profile, you can actually inform the software where to keep the anchorages of the tendon, how many tendons are there in the top flange, how many tendons are there in the bottom flange. So all these things can be given in the wizard. So after the wizard, we get a complete full-fledged bridge ready for you. So all the work which is there for which you do for around half a day or one day will be reduced to a few hours. Okay, so only you need to give some live load to it and do the analysis. So after the analysis, the major results, the major post-processing results that we need are the pre-stress losses. So this shows the balanced cantilever method of construction. So after the wizard, the balanced cantilever bridge is fully ready in front of you with the tendon profile. So the major solution is the major post-processing results that we are interested in is the tendon priestess loss. So the tendon priestess loss, it gives a complete information of all the losses that can occur. So it gives immediate loss considering of elastic shortening, also the friction losses, the anchorage losses, also the losses for creep and sinkage, the relaxation losses. It also shows you the tendon time dependent loss graph for each and every tendon at each and every stage. So in a way we can say that all the tendon profiles can be checked for the losses. Also it will show you the tendon arrangement, how the tendons are arranged inside a section, what is the exit angle at the ends of the section. Also it will show you the tendon elongation. So all the results related to pre-stress you can find in Midas Civil. Also the FCM camber, the camber thing that I was talking about in the previous slides, that you can get the actual camber required during the construction. So what happens is that it will, according to deformation at each stage, the software will automatically calculate the amount of camber that is needed, amount of construction camber that is needed. So at the end of the construction, it reduces the deformation to 0. All the deformation it reduces to 0. So last row you can find it as 0. So you can find the construction camber, okay, and also you can find the manufacturing camber. So both the camber options you can find. So this is all about a balanced cantilever bridge. And what does Midas Civil provide? Okay, so it is quite quite efficient to use Midas Civil because you get all the results, major results, and you get your balanced cantilever done in a very few easy steps. So next is the rail structure interaction. Okay, so why do we need rail structure interaction? So the major thing about rail structure interaction is that whenever we go for metro rails, whenever we go for major metro rails, we have continuous welded rails. Continuous welded rails, what is the difference between continuous welded rails and normal rails is that a continuous welded rail will be a very long rail that is around 200 meters, okay, and it doesn't have in between joints and fissure links. So why is it needed? Because it leads to a reduced impact force. So there is very less impact force from the wheels over the joints and links. Also it decreases the noise and vibration that comes due to the impact force that is generated. So there is a dynamic amplification of impact force when a wheel or rail it runs over the joints. Okay, so these are the advantages, but of course it has its own considerations, own challenges. So what are the challenges that we face? So the key concerns, the major concerns that we face for a rail structure interaction is that track deformation. There is buckling of rail. Because of the temperature, because of the differential temperature, because of thermal analysis, there will be some expansion and contraction. But here there are no joints to allow for that. So there will be very high axial stresses developing in the rails. Due to that, the buckling can occur. Similarly, if the temperature drops, we get split web at the rail end. So there might be some accidents related to that, as you can see in the picture. So that's why we need rail structure interactions. Also, some of the other few considerations that we must keep in mind is when we are doing rail structure interaction, there should be proper interaction between the rails and the deck or embankment. Okay, so the proper interaction means usually if we are working on an embankment, then we will have the ballast between rail and deck, and when we are working on the deck, we'll be having a link, a connection between the rail and deck. So those collections and those ballasts, this should be given some links, some stiffness, okay, to represent the bending deformation of the bridge slab due to vertical load of the rail. Also, another important thing to notice is that when a rail comes, when a train runs over the rail, there are few loadings that we must consider. One is the temperature loading, that is the horizontal loading, the temperature. Also, due to the braking and acceleration of the train, there will be some braking and acceleration load. Also, due to the train loading, there will be some vertical loads. So we need to have a proper interaction of all these three loads. How these three loads will interact with each other. What are the load combinations that we should perform? So Midas Civil can accurately provide the rail deck and rail structure interaction in such cases. It also considers multilinear elastic links as per the loading and unloading stiffness given by the user. It considers the horizontal temperature, braking or acceleration force, and it can perform both separate analysis and complete analysis. I'll be discussing each and every topic in the coming slides. And more things that using rail structure interaction that you can do is that in Midas Civil there is full UIC code implementation. So UIC is the International Union of Railway Codes. So they have given some considerations for rail structure interaction that can be fully simulated using Midas Civil. Also, due to temperature variation, there will be some longitudinal relative displacement of deck. Okay, and the axial force, there will be some very high axial force that will be occurring. That will be more explained in the next slide. Okay, and also due to these high axial stresses, we need to consider some expansion joints at the end of the deck. So to simulate those expansion joints, Midas Civil has a special element called zero lateral radiation element. So you can simulate the expansion joint also using that. So the rail structure interaction for deck and embankment usually occurs in such a way. So usually for embankments you will find that the load that will be coming, the axial load that will be coming will be AE by L into displacement. That will be AE by L into alpha into delta T. Delta T will be the change in temperature. So when the elastic stiffness is there, so they provide some stiffness. The connections, they provide some stiffness. So according to those stiffness, there will be some step graph for axial forces according to the number of resistance provided. Whereas for a continuous welded rail on a bridge, on a deck, now what happens on a deck? To explain this graph, let's consider this thing. So due to temperature, what will happen is that the deck will try to deform in both directions, right? So due to this deformation, due to the rails that are there that are connecting to the deck, these are the connections to the deck. So these rails, they don't allow this deformation. So there will be very high axial stress that will be generating at the ends of the deck. So these high axial stresses, you can find it here. Okay. So these are the additional rail stresses that will be generated in the rails for a continuous welded rails. Okay. So the continuous welded rail on the bridge is usually connected to the superstructure by the ballast, and thus the bridge and the track can interact due to loading. When thermal loading is applied, the expansion, due to the expansion and contraction that is present in the between the bridge and rail, okay, so there will be some axial stresses that will be coming. So what are the different load combinations that we take? So as we discussed, that we have thermal loads, we have the accelerating and braking loads, and we have train vertical loads. Three kinds of loads are there. In the code, in the UIC code, it is mentioned that we simply add up all three loads. Okay, so it over designs a little bit. How it over designs, I will explain in the next slide. Okay, and another type of load combination is that we use a computational analysis method. Okay, so we use a complete solution. We use construction stages. So how to do that? So we will be explaining both the processes in the next few slides. So the accuracy of the rail structure interaction, it will depend on the type of analysis that we choose. So if we choose separate analysis, we apply thermal loading, acceleration of braking loading, and train vertical loading separately. And if we do stage analysis, it will be concurrently applied. So what does concurrently applied means? Okay, so in the next slide in the graph, it will be more clearly explained. Now this graph is actually showing a simplified bilinear curve for the development of track longitudinal resistance force. The longitudinal resistance, by longitudinal resistance force, I mean the force of track per unit length resisting against the longitudinal displacement. So the longitudinal displacement, so whatever force that is needed to resist the longitudinal displacement, okay, that I mean that. So which it will vary depending upon the track structure. It will vary depending upon the loading or unloading and the degree of maintenance of ballast, a ballast-less track or a track installation method, the loading frequency. So to account for all those non-linear behavior of interaction, we give multilinear elastic links. Now for separate analysis, if we consider the separate analysis, simplified separate analysis method, so in a way what we can say, there are two types of stiffnesses. One is the unloaded stiffness, okay, and one is the loaded stiffness. So what do we mean by unloaded and loaded stiffness? Unloaded stiffness means that when there is no train loading over when there is no train load over the rail, in that case the connections, the ballast will have some unloaded stiffness, some stiffness due to the temperature. Okay. Similarly, loaded stiffness is that when the train load is coming over the track, then the ballast or the connection will have some different stiffness. So there are two types of stiffness. One is unloaded stiffness and one is loaded stiffness. So both these stiffness will follow a separate graph. Now in a separate analysis, what we do is that we consider the unloaded stiffness separately. So initially from the starting point, it follows the unloaded stiffness graph and reaches the thermal alone point. So this is the thermal alone temperature point where only temperature stresses are activated. After this, we consider the initial condition of the bridge again, and then we apply the train loading separately. So again the loading will follow the resistance, will follow the loaded stiffness. Okay, so if we say that the unloaded stiffness is 20 kilonewton per meter, okay, and the loaded stiffness is around 40 kilonewton per meter, so the total stiffness that will be generated in the links will be around 60. So in a way it doesn't give the proper interaction between the unloaded and loaded stiffness. Whereas in a complete analysis, what will happen is that initially, due to unloading, when there is no load there will be the resistance will follow the unloaded stiffness. Okay, so due to the unloaded, where it reaches the thermal alone point, now the program will consider the deformation as it is. So whatever deformations, whatever stiffness that has been occurred, that is there due to the unloaded stiffness, will be remained at that place itself. Okay. Now when we add the loading over the bridge, it will continue from the thermal alone point with the loaded stiffness slope. So in a way, we get the final as 40 kilonewton per meter. That should be there accordingly. So we over design a little bit if we do separate analysis. Complete analysis gives you a perfect interaction between the unloaded stiffness and loaded stiffness. So in a way I can say that when the train load is applied, while the train load in the complete analysis is applied, while the displacement and the internal forces due to the thermal load that we have considered, they are maintained. It is not coming to the original state, they are maintained. The resistance then switches from loaded stiffness, switches to the loaded stiffness curve and over the road bed where the train load is applied. Okay, so the horizontal resistance follows the loaded stiffness curve from the thermal alone point, from this point, but the limit is from the origin to but the limit will be from the origin to the limit of resistance of the loaded track. Okay, so this can be properly simulated using construction stage analysis. So in the computational analysis, what are the considerations that need to be taken? Now, if you have understood what I've explained in the last few slides, then there are many considerations that comes to our mind. One is that for a rail track analysis, for continuous welded rails, I need to consider the full span. I cannot work on just one span and go above and check the result. I need to consider the full span. Also, whenever the loading is there, suppose my train loading is somewhere here. Whenever the loading is there, so underneath this loading, whatever elastic links, multilinear elastic links that we are giving for the connection to simulate the connection, this should have the loaded stiffness. Okay, this should have the loaded stiffness, and rest of the track should have unloaded stiffness. Okay, now the train position is not fixed, so it can move here also. This train position can shift to another position also. So we need to convert the stiffness from loaded, unloaded to loaded for all those train positions. So it becomes a little difficult. Also, if we consider the distribution of forces from the loading from the vertical loading, it will distribute to the piers, and also from the loading it will distribute to the embankment. So it will be a combination of horizontal and a vertical force. So we need to have a multilinear elastic link to represent that stiffness. Of course, it will have a non-linear behavior. So we need to consider a multilinear elastic link. So it becomes the simulation of such problems, it becomes quite difficult. So what can we do in such cases? So the considerable amount of effort is required. So there are a number of train loading positions, and we provide the unloading and loading stiffness to each link. So this changes with the loading position of the train, as I explained. Okay, and also the full complete modeling of deck and embankment is required, and providing proper multilinear links for the connections and ballast to simulate the connection and ballast. So how does Midas Civil fit into all these considerations? How does it help an engineer to choose what kind of considerations, choose what should we do with the solution that is there? So Midas Civil will automatically generate the full model for you. So the modeling, which requires around a day or 2 days or 3 days for different models, Midas Civil will automatically generate the models. Also, for the loading and unloading stiffness, it will be automatically provided as per train loading. So you define some iterations, so you define some increments that my train loading will be given in some increments of distance. So in that case, Midas Civil will automatically give the loading and the unloading stiffness as per the train loading. So it will automatically generate a number of models and give the loading and unloading stiffness. This reduces the task of 2 to 3 days to probably half a day. Okay. So for Midas Civil, how we do it? So we have a proper rail structure interaction. So this is how you give a multilinear elastic link. Okay. So the rail is connected to the deck using a multilinear elastic link here. Similarly, the centroid of the deck is connected to the bearings using another rigid link. So the simulation of the practical problem is done by a line element model, and then providing elastic links to replicate the unloading and loading stiffness of the ballast and connections. Similarly, we can do dynamic analysis of a high-speed train. So what do I mean by dynamic analysis? That you can actually provide the time step functions, dynamic time step functions of force. You can give a dynamic force, and you can find proper results. Results for each and every time step. How the track is, how the deck is behaving for each and every time step you can find. Also, finally, we check on the rail track analysis model wizard. So we have specific wizards for rail structure interaction, where you can model the temperature load, the train load and train acceleration or braking load together with the construction stage of all these load cases. So it can do both separate analysis and the complete analysis. Moreover, as I told you, it will have auto generation of multilinear type elastic link. So all the multilinear type elastic link will be automatically generated. Also, depending on the load of the train and depending on the number of increments that you are giving, it will automatically generate the models also with the specified loading. So next we discuss the integral bridge. Now in this metros we consider the rail track analysis, we consider the balance cantilever. So why and when do we require integral bridge? Integral bridge, majorly it has been used very efficiently in the monorails that has been recently started in Mumbai. So that's why I try to touch this topic a little bit. So why do we need, what is integral bridge and what are the considerations? Okay, why do we need integral bridge? So we have a monolithic construction. So in a monolithic construction, it means the deck and piers are monolithically constructed, and that or the deck is integrated with the pier afterwards. So more or less we cannot see a bearing in between. There is no bearings at all. So it comes as a portal frame behavior. Also, it is quite cost effective, as there are no bearings, there will be very less maintenance that is required. In the integral bridge, the construction sequence becomes very important, because as per the construction sequence, the loads will be transferred from the deck to the it will be in the same way it will be transferred. So the construction sequence, it becomes very important, because as we change the construction sequence, you will see a different result. Also, the temperature effects, because integral bridge there are no bearings to allow the temperature deformations or anything. So in that case, we need to consider proper temperature effects. So we need to consider, suppose we can give the outer piers can be more flexible than the inner piers. Okay, and then one of the most important thing that needs to be considered in an integral bridge is soil structure interaction, because we need to apply the soil stiffness of the adhering soils to the piles and the abutments. Okay, because the soil has a non-linear behavior, so when there is a proper integrated bridge, it will affect the structure a lot. So we need to have a proper soil structure interaction for the foundation that we give. So the major integral bridge type will be somewhat like this, where the deck is more or less integrated with the piers. So this is the common type of integral bridge. So integral soil profile. So usually you find a soil profile like you have the cohesion factor, the undrained shear strength, the elastic modulus. So usually what you do in your normal day-to-day design is that you consider this soil profile, okay, and you find the subgrade reaction, and from the subgrade reaction we find the soil stiffness, and then we provide it to the structure. So how does Midas Civil just ease out this process? Okay, so in Midas Civil we have a non-linear point spring support which can exactly replicate, which can replicate the stiffness of the backfill and the soil. So in this we have one pile spring support, this is a pile spring support, and this is abutment spring support. So in this you can enter the soil type, what is the ground level, what is the pile diameter that is there, what is the unit weight of the soil, what is the cohesion of the soil, what is the subgrade reaction of the soil. So accordingly it will automatically generate all the spring supports. Also you can consider the non-linear behavior, like if you are considering the damping of the soil due to the soil stiffness, so you can consider a general link for soil structure interaction. Okay, so it is Midas Civil is suitable for the structural engineers whose main interest is to check the stress and deformation of structures. The geotechnical engineers, however, are more interested in the stress and deformation of the soil itself, right? So for this purpose, we need to include proper, stiffness of the soil and everything. So you can interact with another software of Midas, that is Midas GTS for that, for a more advanced analysis of the non-linear behavior of the soil. So this is how the soil spring supports is completely generated. It is automatically generated as per the wizard, as per the dialog box that we saw. So we can see the moment diagram for the self weight. So you can see the self-locking capacity of the integral bridge. So where the self weight is self-locked within the deck itself. And also due to thermal expansion, you will find the moment diagrams. So Midas civil is actually very popular for the integral bridges, and integral bridges is now an upcoming boom in the engineering field, because most of the bridges now being considered are moving towards integral bridges. So the next topic will be tunneling. So I will be briefly discussing the tunneling also, because in metro rail we are not only going for bridges, we go for tunneling also, right? So in that case, what is the solution that is given by us? So in tunneling, while tunneling for a geotechnical engineer, one of the major consideration is the settlement, because when we bore a hole inside the soil, I mean when we go for tunneling, there will be some surface settlement. So we need to properly consider the settlement of the soil at the top surface. Also, tunneling, when we are doing for metro structures, it will be done within the urban settlement, right? So we will have some adjacent structures like deep foundations, adjusting tunnels, and all these things. So when we go for tunneling, it will affect the adjacent structures also. And the actual simulation of the surface and the soil should be performed. The actual simulation, how the soil and structure will, how the surface, how the adhering soil, what will be the stress generating in the soil layer above and below. So all these things need to be considered. Also, the construction sequence of the tunneling becomes one of the major considerations. Okay, so I mean, how you are going about the tunneling, how you are constructing the tunneling, what method you are applying. Okay, and after that, the pressures, the earth and rock pressures, the water pressure that is coming. Okay, so for this we have Midas GTS. Midas GTS NX, actually it provides a complete replicate. It replicates the complete actual geometry of the ground. So whatever actual geometry that is there in the ground surface, it can be replicated using Midas GTS. So Midas GTS is actually having one special tool called Terrain Geometry Maker. So using Terrain Geometry Maker, you can replicate the exact ground profile. Also, you can also replicate the underneath layers using the borehole plane wizard. So using borehole test, whatever depth you have found, you can insert into that, and it will automatically replicate the internal depths also. Another important feature for Midas Midas GTS is the tunnel generation wizard. So using tunnel generation wizard, again you have got the layout for the profile. For the profile of the soil, for the different layers of the soil, the strata condition, the groundwater condition. Also, you can do the different type of tunnelings like circular tunnels, semicircular, okay, horseshoe shape, and finally you get the full model ready in front of you with the construction sequences and everything. So you get the settlement due to tunneling, all the settlement, the major consideration that is there for the settlement, for the tunneling. So you get the crown settlement at different stages and the vertical displacement associated with the settlement. So tunneling in Midas GTS, it can be done in a fault zone, factored zone, also some interconnected tunnels in between. If there are sealed tunnels, you can simulate the sealed tunnels also. Also the steel pipe, reinforced step grouting. So all these things, all these type of tunnelings can be done using Midas GTS. So next we will discuss the metro rail project applications. So we have discussed, till now we have discussed the balanced cantilever method of construction, the rail track analysis, the integral bridge, and tunneling. So how all the clients, all the major engineering companies, they have used these solutions to go about for their own project application. So you can see here the Chennai Metro. This is a curved segmental bridge. So you can see the rail and the deck model. Okay. So the same model is replicated here. So this is the Midas civil model. for the Chennai metro. Similarly, we have the Hyderabad metro, which is again a segmental bridge. Okay, and then we have the Delhi metro, which is again a balanced cantilever method of construction. Delhi metro. Majorly AECOM is dealing with this. Then we have the Mumbai monorail. So the integral bridge type, this is the type of integral bridge. So you can see here that the pier is integrated with the deck. Okay, so full integral bridge was done in Midas Civil itself. Mumbai monorail. Sorry. And also this is the Mumbai monorail station that has done in Midas Civil itself. So they check the stresses that is generating in all the structures, adhering structures. So this is the Mumbai monorail station. And few of the international projects. So you can see this is the light rail transit in Canada, PSC box section. Also a viaduct bridge in Italia done by Midas Civil. Also the Tarango bridge in Mexico City, Mexico. So you can see that there is an intersection also that has been simulated in Tarango bridge. So at the end, why Midas Civil? I mean, you have understood the solution that we have provided. So what are the other things that Midas covers? So Midas Civil is actually, it provides a wide detail of application areas. So where you can perform analysis from very basic bridges to very complex bridges. So in that you can go for very basic like box culvert bridges, segmental, box culvert, PSC box, and also composite bridges to some advanced analysis options. So you can go for segmental post tension bridge, construction stage analysis. Also we have a 3D tendon generation wizard in the newest version, in the latest version, where the tendons can be generated, or where the parabolic profile can be automatically generated. Also we have got PSC girder design, the dynamic nonlinear analysis. So all these are the options available with the engineers. They have got all the analysis options. They have got all the kinds of bridges that can be done using Midas Civil. So what kind of bridges that Midas Civil handle? So it can do the most conventional bridges like culverts, slab bridge, integral bridge, to most segmental bridges like stage segmental bridge. So it can handle not only balanced cantilever, it can also handle the incremental launching bridge, movable scaffolding, precast segmental bridge, and full staging method if you are constructing in the general way. Also, you can do very complex bridges like cable stayed bridge and suspension bridge, which requires very complex stresses, very complex phenomena, very complex analysis like large displacement analysis of rails and everything, of the cables. Okay, so all these type of bridges can be handled using Midas Civil. Apart from that, we have an active technical support team which can give you technical support throughout 24 hours. So these are the major technical team that is there in Midas. So we also go for online training. We usually hold such webinars like this. We also do online training. We also do offline training, and also we organize events. We organize conferences and seminars throughout the world. So this is about Midas. What all the things you can expect from Midas. So finally we come to the summary. So I hope that you have understood all the methods that can be used in metros and how it can be done using Midas Civil. So to summarize what we have done in the webinar, so we discussed the balanced cantilever bridges. We also discussed the integral bridges. What is integral bridges? What are the due considerations? What are the different applications of integral bridges? Okay, and how it can be simulated using Midas. We also discussed rail structure interaction. I gave you a brief about rail structure interaction and explained a few points about it. So the rail track analysis module, the rail track wizard also. I explained the unloading and loading stiffness. What is the use of unloading and loading? How the thermal stresses and the vertical and horizontal loading can interact with each other. Why the rail track interaction is needed. Why is it needed in continuous welded rails? Okay. So what is the use of that? So all these things we have discussed, and we also discussed a brief about tunneling using Midas, GTS and X. So in the next webinars, in this webinar it was just an introduction. So in the next webinar we will more or less focus on rail structure interaction. So on 6th June 2014, the webinar will be done by one of the most professional clients of L&T ECC. So it will be conducted by Mr. Nitin Mittal and Akshay Vahal, who is the assistant manager in L&T ECC. So they will be covering rail structure interaction, the introduction to rail structure interaction, the most theory and concepts, what are the concepts, and what are the things that should be considered while we are simulating the rail structure interaction. And the most important thing is that they'll be discussing some of the projects that they have done using Midas Civil, using the rail track analysis feature of Midas Civil. So they will be discussing that project. So you will learn how all these things have been done using Midas Civil. Also, in the last webinar that will be again conducted by me, so on 10th June 2014. So in the last webinar we'll be taking the rail track analysis in Midas Civil. So I will be showing you a live modeling using a wizard section, how the UIC code can be implemented. I will also show you the separate analysis and complete analysis. So complete stage analysis, separate analysis, and then some of the results like axial stresses. How can we interpret the results? What are the different things? What are the different, what are the solutions that we get from the results? So I'll be discussing that in the final webinar in this series. So I hope that this webinar was useful to you. You got some technologies related to metro projects, and please join the upcoming webinars that will certainly increase your aptitude for rail track analysis and will help you for your metro projects. And for any further queries, and if you have any doubts, you can always mail us. You can always come back to us at techsupport@midasit.com. This is our email ID at present. So you can always come back to us at techsupport@midasit.com. So hope you liked the webinar today.